Hello again, everybody, and welcome back. This is example 9.4 in our chapter on potential energy and work. And this is sort of a practical example because I think at some point we all care about how much work we have to expend in order to burn off an item of food. All right? And the item of food right here is a Snickers bar that has 271 calories of energy in it. All right, calories are a unit of energy. I'm not going to go into the difference between a regular food calorie and a regular heat calorie and a regular food calorie. I'm just going to give you a conversion for that. But let me see if I can shrink this down here and give us some more space, and I'll show you what I mean by that. So, one food calorie. We're just going to call it a calorie, not worry about the fact that it's a kilocalorie. 1 calorie in food is 4,184 joules of energy. All right, so that means you need to expend a certain amount of energy to burn off a calorie that is in food, no matter what kind of food it is. That amount of energy is 4,184 joules. Okay, so if a Snickers bar has 271 calories in it, 271 calories. Let's do a quick conversion right here. It's 1 calorie to 4,184 joules of energy right here. The question is, how much energy really is in that Snickers bar? All right, well, I get 271 times 4,184. I get, goodness, that's a lot. That's, I'm doing this kind of live here. 1.13 times 10 to the 6th joules of energy. All right, that's 1,133,864 joules. So I'm just going to abbreviate it to 1.13 times 10 to the 6th joules. So that's a decent amount of joules of energy that you need to expend in order to burn that off. All right, that's the amount of energy that's in that. So, what's our working equation for this? Well, the working equation that we've been using is potential energy due to gravity initial equals potential energy due to gravity final plus the work done by gravity. All right? Gravity being a conservative force right there. All right, well, if we've got a girl climbing a set of stairs, and I'll draw her over here. All right, so here's our stairs. And the question is, how many stairs does she need to climb? And we'll get to that in just a second. I'll draw her down at the bottom here. There's our girl. And here she's at the top right here. Don't know how high up she climbed. Where does she have more potential energy? Okay, this is our initial. This is our final. Well, I think you probably agree that at the top right here, she has more potential energy. If these stairs ended right here, she would have the potential to fall down, right? So there's greater potential energy here than here. So if we look at our working equation right here, that right there, if there's greater potential energy finally than initially, then what does this mean? Final plus something equals initial. That means that gravity must be doing negative work, right? If she's moving upwards, this is a lot like the mountain climber problem. Okay, gravity's acting against her, and gravity's doing negative work, and she's working against gravity, and therefore expending the energy that was in the Snickers bar that she ate. Okay, so how much work is gravity going to have to do against her in order to burn up all of that Snickers bar? All right, well, that's going to be minus 1.13 times 10 to the 6th joules of energy. Right, that's how much the gravity needs to work against us, right, or work against the girl. So we can say work due to gravity equals potential gravity initial minus potential energy due to gravity final right here. Well, the nice thing about this difference right here is the fact that it doesn't matter where you start. For example, we said before that you can find the potential energy at any one point by saying this is mgh initial and this is mg times h final right here. But since all we care about is really the difference or the height right here, then we can say, hey, why don't we just call that 0 joules? If that's the case, then we can say that the work done by gravity, or really the negative work done by gravity, is minus the final position or the final potential energy, all right? The final potential energy position that it has. Okay. So really, what we're saying here is that the girl must climb a set of stairs and haul herself up those stairs, her 50-kilogram self up those stairs, to a certain height such that it burns off the energy that she ate. Okay. So we'll take those minus signs away, and we'll just say the work that we care about is really the final potential energy that she has, assuming that we called the ground level 0. Okay? Well, this makes it a little bit easier. All right, so 1.13, well, you know what? I'm not going to do that quite just yet. I'm not going to plug anything in. I'm going to write our equation right here for final potential energy, and that's mg times h final. Right? And if we're solving for h final, work due to gravity, we're going to divide by m and g, and so our working equation for the final height is work done by gravity divided by the mass of the girl times gravity. All right? This is a subscript g. That's an actual g right there. Okay? So what's the work that has to be done acting against her by gravity, or the work that she has to put out so that she burns off the Snickers bar? That is 1.13 times 10 to the 6th joules. Let's divide that by her mass times gravity. So 50 kilograms times 9.81 meters per second squared. All right, that gives us a height of what? 1.13 times 10 to the 6th divided by 50 times 9.81. That's 2,303 meters. All right. Oh goodness. All right. That's pretty high. All right. So the question is, how many stairs does she have to climb? All right. Well, that's pretty easy. We're just going to do some dimensional analysis right here. I'm going to do this kind of up in the corner. If our final answer is, I'm going to kind of dotted line box that, 2,303 meters, all right, and 1 meter equals 100 centimeters, all right, and centimeters to stairs it's 20 centimeters per one stair, and that should give us an answer that is in stairs. All right, so here's how many stairs she's going to have to climb if stairs are 20 centimeters tall. So 2,303 meters times 100 divided by 20. That's going to be 11,515 stairs. And that's our answer right there. 11,515 stairs she has to climb just to burn off that Snickers bar right there. And that sounds like a lot. But there's a lot of energy in Snickers bar, and every set of stairs is about 12 to 15 stairs. So a couple, I don't know, go up and down a flight of stairs, and that would burn that off. The other thing that we're not accounting for is the fact that your body uses up energy whether you realize it or not. Your brain uses energy, your heart does. So just thinking and moving around burns up energy. But if she did nothing else, she would have to climb 11,515 stairs just to burn off that one Snickers bar. So it kind of gives you an idea of how much energy is in the things that we eat and how much energy we use on a daily basis. So that's example 9.4. I hope that helps. And if you have any questions, please make sure you see me. In the meantime, I'll look for you on the next one. Thanks for watching.